Hello all of you. Welcome to the third week of lectures in the course on analysis and modeling in chemical engineering. In the previous week, we have discussed some of the fundamental laws and concepts in chemical engineering and what is the intercorrelation between them, how they are connected together. So, in this week, we will sum up that part by discussing the idea of phase equilibrium, and from the phase equilibrium onwards, I will introduce the idea of degree of freedom of a multi-component multi-phase system. And going further in this week, we will cover the representations of a chemical process, what is known as flow sheets, different kinds of flow sheets, and how to perform process simulation on a computer. Although the idea of this course is to focus on the concepts that are used in modeling more than the actual simulation software, but nevertheless, I will introduce you to some basic concepts of how things are done on a computer. So, this is what where the phase equilibrium story begins. So, if you think about it, I have already talked about how entropy is important and how it causes mixing. I took an example of case where we had like two chambers containing a gas. In the beginning, the all the gas is there only in the left chamber, and there was a valve which was closed, and if I open the valve, then the gas moves between these chambers, and then eventually it is entirely full, right. So, basically this whole notion of mixing, and then we also took an example of nitrogen and oxygen mixing together to form air. This whole notion of mixing comes from the idea that entropy of the system need to be maximized, and therefore mixing is supposed to be an easy process. And if I now think about the opposite of mixing, that is to separate, it should therefore be a more difficult process. If entropy favors mixing, mixing results in higher entropy. So, if I try to separate now, that would result in a lower entropy, and that will be difficult, right. We can do an experiment very easily. Let us say you have a cup of tea and you add sugar in the cup of tea. Mixing should be fairly easy unless you go to very high concentrations of sugar. But on the other hand, once you have mixed that sugar in tea, then to separate that sugar that is dissolved, it is not going to be easy. You can try to use a strainer and try to take it out. It won't come out unless you have very high concentrations of sugar and it is precipitated. So, separation is therefore going to be a very, very difficult process than compared to mixing in this case. And again, the reason being is that entropy is no longer on your side. That means whatever process you are trying to do, the separation process, it results in a lower entropy, and therefore you have to supply good amount of energy in order for that to happen. On the other hand, for mixing, you may require to give less amount of energy, and even if you don't give energy, the sugar will eventually mix with tea. It will take more time. So, by stirring it, you are expediting the process, but entropy is always favoring the mixing. That will happen even if we do not stir. But this is not always the case. Let us say, for example, you have an oil and you are trying to mix in water. Now, I repeat the same experiment, and what you will find is mixing of oil and water is going to be difficult. You can try to stir it. If by lot of effort you can manage to stir it, it will look like solution of oil and water, but as soon as you stop stirring, the oil will separate and the water will separate, and you will have a perfect phase separation between oil and water, right. In common parlance, we call it because oil and water is immiscible. But what is that causes immiscibility? Where does our analysis based on entropy goes wrong, right? So, now the reason for this is, although I have said that the higher entropy is favored, delta S greater than 0 does not always guarantee mixing, right. It is true that the second law of thermodynamics says that the entropy of the universe is always increasing, but that does not mean that the entropy of a system cannot increase, because you have a system and the surrounding, right. So, now what we have also said is, depending on the conditions where I am doing the experiment, let us say I am working in the conditions where temperature and pressure is being held fixed. In that case, what instead should be true is my Gibbs free energy change should be less than 0, or Gibbs free energy should be minimized. And now if I look at the Gibbs free energy change, at least for any system, it is going to be something like the enthalpy change minus temperature times the entropy change, right. So, we have written earlier G is equal to H minus Ts. So, if temperature is held fixed, in that case we can write as it is written here, delta G is minus delta H minus T delta S, right. And now you see that now we have two terms. The second term is always negative, because entropy change, if I am trying to mix it, it is going to be positive for the case of mixing. For separation, the entropy change is going to be negative, right. But this delta H, the enthalpy change, is going to be positive if you have immiscible liquid, right. And if delta H is sufficiently positive, and if the magnitude of that is more than negative of T delta S, in that case you can imagine that the net quantity is going to be positive, right, and therefore mixing may not take place, right. On the other hand, the opposite may be true. Let us say, for example, things have a tendency to phase separate. In that case, delta S is less than 0. So, the second term here is negative, but if delta H is negative, sufficiently negative, then delta G can still be less than 0, right. So, we cannot always take this argument that the entropy always favors mixing. It does, but then there are other things in this problem. There is enthalpy change that also need to be considered, right. And that is the reason why the oil and water does not mix so easily. So, I will take this argument further, and I will kind of question one of the common argument or common thing that you may have learned in mass transfer course, that whenever we have a concentration gradient, it results in mass transfer. Now, you take the same example which I just gave. So, you have oil and water, which is kind of separated because they are immiscible for the reasons I told you. And now you see here, if I look at the concentration of oil in the oil phase, on the top phase, it is pretty high. So, there is plenty of oil here, and there is very little oil here. Let me call this oil phase and this as water phase, right. So, this concentration of oil is much bigger than the concentration of oil in the water phase. Pretty much there is no oil in the water phase, right. So, therefore, there is a concentration gradient for the oil, that if our argument of concentration gradient resulting in mass transfer is true, it should result in oil getting into the water phase, but it does not. Oil does not want to go there. There is some kind of an invisible barrier. If we do not take it very at a fundamental level, it may appear that the oil is not getting there. There is a principle that tells it to go, the concentration gradient is there, but it is still not going, right. I can take a counter example. Let us say, for example, somebody smoked a cigarette and there is lot of smoke out there. By the way, cigarette is injurious to health. So, there is plenty of smoke there, and now somebody, if it is doing there and it is, let us say, in an open room, then all the smoke is going to fill that entire room and will get diluted when it is doing that. So, in that case, near that cigarette, the concentration of the smoke is pretty high, and in the room otherwise the concentration of smoke is pretty low, and smoke is able to pretty much fill the room. Pretty much the same example as we had for nitrogen or oxygen coming together and making up air very easily, spontaneously, right. So, what exactly went wrong? This idea that concentration gradient result in mass transfer is not generally valid. What I am going to propose is that it is not the concentration gradient. In fact, it is the gradient of the chemical potential that results in mass transfer, right. In this particular case of oil in water, although there is a concentration gradient, there is no gradient of chemical potential available for the oil to go from here to there. And in this case, the concentration gradient is also resulting in a chemical potential gradient, which is what gave rise to smoke filling up the entire room. So, now I hope I have been able to convince you therefore is that it is not the concentration gradient or anything else. We should look at this Gibbs free energy, right. And in fact, chemical potential also is related to Gibbs free energy. So, for a single component system, mu is the partial molar Gibbs free energy dou G by dou N at a constant temperature and pressure. Typically, we talk about multi-component system where, let us say, for component I have mu I as dou G by dou Ni at constant T, constant P, and all other species, their numbers are not changing, right. So, now this is this chemical potential or this Gibbs free energy that dictates whether any two liquids or any two things are going to mix together or are they going to phase separate, right. So, let us now do this kind of an experiment, but before we do that, there is one other thing I want to introduce here is the notion of equilibrium, right. And equilibrium here means absence of any external agency, right. So, for example, you have oil and water. If I really put a lot of stirring in the system, if I provide energy in the system by means of stirring, I can manage to mix oil and water, but that is not the state of equilibrium. That state will be disturbed as soon as we remove this stirrer. The system will then go back and oil and water will separate, right. So, I am referring to the condition of equilibrium as the condition where there is no external agency and then eventually there is no change in the concentrations because concentration gradients should eventually vanish. In both the examples which I gave here, in the case of oil and water, the concentration gradients are not there in the oil phase, and even though the concentration gradient is there at the interface between oil and water, it is not going because of chemical potential, but within the oil phase there is no gradient, within the water phase there is no gradient, and in here as well, eventually once the smoke fills the air, there is no concentration gradient, right. So, this chemical potential gradient is going to eventually vanish, and in the case of smoke, it is equivalent to saying that the concentration gradient also vanishes, right, and that is the condition of equilibrium. In the case of oil in water, the concentration gradient remains at the interface, but chemical potential gradient vanishes. So, what is more important therefore, is the chemical potential gradient, not the concentration gradient. So, now I do this experiment where I mix two different liquids or gases or any other thing, but we will confine ourselves to liquids because it is easier to think of. And let us say they have some initial concentrations of two species Ca and Cb, and I label them as Ca1 and Cb1, and let us say the volume of that is some V1, and I have another vial or another test tube containing another concentration Ca2 of component A and Cb2 of component B and another volume V2, right. So, when I now put them together, assuming that there is no volume change upon mixing, in reality there may be a volume change and we can consider that, but let us say I want to take an argument that the volume change is not there on mixing, which is not such a bad assumption for the case of liquids anyway. So, the final thing will have a volume of V1 plus V2, but then it can either be in a homogeneous phase, that is well mixed phase, or as a phase separated state where there are two phases in equilibrium, right. And one phase naturally will be rich in A and other phase naturally will be rich in B. In the extreme case of oil and water, there is pretty much no water in the oil phase and no oil in the water phase, but in general you can have some amount of A in the B rich phase and some amount of B in the A rich phase, that is quite likely, right. So, when it is completely mixed together, you form some concentration, final concentration Ca and Cb and some Gibbs free energy of that, and when it is phase separated, then you have two phases, and I now use different subscript purposely V1 and V2 in Roman subscript. The reason being that these are not the same as the original volumes of the two liquids which I started with, right. So, in the condition of equilibrium, this is the volume of, let us say, A rich phase, and the other one is a volume of B rich phase, right. And now, which of these is going to happen? Whichever gives me a lower value of the Gibbs free energy, right. So, let us say, for example, G is the Gibbs free energy in the mixing case, and G1 is the Gibbs free energy of phase 1 here, and G2 is the Gibbs free energy of phase 2 here. So, it turns out that the Gibbs free energy is an extensive property, it depends on quantity, it is also additive, right. So, therefore, the net Gibbs energy of the system is G1 plus G2, and if G1 plus G2 happens to be less than this G, which is found upon mixing, in that case it is going to phase separate, because the system will try to keep its low Gibbs free energy to a lowest possible value. On the other hand, if G upon mixing happens to be less than G1 plus Bg2 on phase separation, then the system will mix together, right. So, we have now written the argument in terms of the Gibbs energy, and now you know that the derivative of the Gibbs energy with respect to the number of molecules is my chemical potential. So, now I will extend the same argument in terms of chemical potentials. So, now let us say you have these two phases. I am assuming with a situation where we have phase separation, and then I will show you how we can describe the mixing case. So, let us say there are these two phases 1 and 2, and let us say they are not right now at equilibrium, they are going towards equilibrium, right. So, when they are not in equilibrium, then there are chemical potential differences or chemical potential gradients which are present in the system, and chemical potentials are defined for each component in each phase. So, let us say, for example, chemical potential of component A in the phase 2 happens to be higher than the chemical potentials of A in phase 1. In that case, the gradient of chemical potential exists in the direction going from phase 2 to phase 1. There is a higher chemical potential in phase 2 of A and lower chemical potential in phase 1 of A. So, A will go from top to bottom, 2 to 1. Let us say delta Na is the number of moles that is going in that small time, right. So, I am switching from number of molecules to the number of moles. It is only a difference of a factor of Avogadro number, that is a constant anyway. And now what I say is, for B it is opposite. For B, the chemical potential of B in phase 1 is higher and chemical potential of B in phase 2 is less. So, therefore, chemical potential of B exists in the reverse direction. So, B will go from 1 to 2, this is the direction of B, and A will come from 2 to 1, and let us say delta Nb is the number of moles of B that is transferred, right. Now, one thing you keep in mind, that the chemical potentials are not constant. Chemical potentials depends on the composition. So, as soon as there is a transfer of molecules or moles of components from this phase to the other, chemical potentials are going to change because they are composition dependent. We have taken the temperature pressure constant, but there will be a composition dependence. In general, chemical potential will depend on temperature, pressure and composition. So, as soon as the molecules or moles go from one phase to the other phase, the chemical potentials will change. So, therefore, I am referring to a small change delta Na, and over that small change delta Na of A and delta Nb of B, I am assuming that the chemical potential remains constant. So, now the change in the Gibbs free energy delta G is given as sum over I mu I delta Ni. How do I get it? I have earlier written dG as minus S dt plus V dP plus sum over I mu I dNi. We are working at constant temperature and constant pressure. So, I am going to drop the first two terms and we only have last term remaining here. So, for a small change delta G, we will have sum over I mu I delta Ni. And I know what is this delta Ni for both A and B and what are the chemical potentials. So, let me plug that in here. So, for component A, mu A1 is the chemical potential in phase 1 and things are coming to phase 1. So, delta Na is the number of moles which is gained by phase 1. So, this is, I put a positive sign there. On the other hand, the phase 2 loses the same delta Na moles of A. So, there is going to be a negative sign here therefore. And for B, the phase 2 gains Nb moles of B and phase 1 loses Nb moles of B. And now I can rearrange this equation and it becomes something like this with a net negative sign in the front. What this means is, since the way we have defined it, delta Na is higher than 0 and delta Nb is higher than 0. So, therefore, if this quantity is positive, which is what we have assumed here, and this quantity is positive, which is what we have assumed here, the delta G is going to be negative, which is a favored process, right. So, this will keep on happening, the molecules or moles of A and B will keep on transferring in this particular fashion. Eventually, it is going to stop somewhere, just like chemical reactions, right. So, if you have a reversible chemical reactions, the forward and reverse reaction will keep on happening until a point when we reach chemical equilibrium. In this case, there is no chemical reaction, but nonetheless the idea is very similar. The molecules of A or moles of A and B will keep on transferring until we reach some kind of a minima of the Gibbs free energy. And when will that happen? When the chemical potentials will become equal for both the components in the two phases. So, chemical potential of A in phase 1 is equal to chemical potential of A in phase 2, and same is true for B. And in that particular case, now there is no driving force. In this case, delta G will go to 0. That is pretty much, you may recall the diagram which I have given earlier, something like a minima of G with respect to the extent of reaction for the chemical equilibrium, something very similar to that. Now, we have reached this minimum point, and at this minimum point there is no net mass transfer, delta Na and delta Nb will go to 0. So, very similar to the notion of chemical equilibrium, we now have a phase equilibrium, right. Now, in here we have, in the experiment that we have I've just shown you, I have assumed that there is a phase separation. When will mixing happen? The mixing will happen when this continue to happen until one of the phases vanishes, right. So, let us say, for example, if I had taken this 1 as the cigarette example that I just gave and B as the room, then the smoke will keep on filling the room until all the room is filled. So, in that case, what is going to happen? One of the phases is going to completely vanish, or both the phases become 1, right. The same picture can therefore be used to figure out when the mixing will happen and when the phase separation will happen. And in that case, what we also have is a gradient of mu is basically translating into a gradient of C, because eventually the gradient of C is also equal to 0 in the mixing case. In this case, however, in the phase separation case, the gradient of C is not equal to 0, the oil water example whichever I gave you, right. So, therefore, I hope I have managed to convince you that it is not the concentration gradient, it is the chemical potential gradient that is the actual driving force for mass transfer. So, now there is one other thing that we have assumed here, that the temperature and pressure is constant. Let us say if I begin with some temperature difference in the two phases, what is going to happen is that because of the temperature difference, there is going to be also some flow between 1 to 2, the kind of thing flow that you see when you boil water on a stove, right. So, the bottom part of one water gets heated up, its density becomes smaller, and then it goes up by convection, and then the top part, it becomes heavier, it comes down, and again water is getting from top to bottom and bottom to top, but there that driving force is not actually chemical potential, there the driving force is a temperature gradient. So, temperature gradient can also drive flow. Similarly, if the pressure is not constant, you have some pressure in the bottom and some pressure at top, the pressure gradient may also drive flow. In fact, that is what happens in a pipe flow problem, right, because of the pressure that I supply and there is a pressure drop along the pipe, the flow does happen, right. So, in principle, we also want to stop those processes, the heat transfer and this mechanical pressure driven transfer or flow. I also want to stop that in order to reach equilibrium, and that means a condition of thermal equilibrium and mechanical equilibrium, right. So, if I do, let us say, start with a hot oil and in a cold water. So, now in the beginning the temperatures are different, the pressures can also be different in principle, but temperature definitely are different and chemical potentials are also different. So, in that case the temperatures need to become equal, pressures need to become equal, and chemical potential of both oil and water in the two phases should become equal, right. So, for oil it should be chemical potential of oil in the oil phase, chemical potential of oil in the water phase, right. Now, you can say that okay, water contains no oil, how we can define the chemical potential, right. That is defined in the limit when the concentration of oil goes to 0 in the water phase. In reality, it does not happen. There is always some molecules of oil that manage to be in the water phase. So, it is a valid definition nonetheless, right. So, we are going to have therefore three conditions: a thermal equilibrium, a mechanical equilibrium, and finally a chemical or phase equilibrium. I will prefer to call it just the phase equilibrium, just to emphasize that there is no chemical reaction, but in reality it is because of the chemical energy. But just to emphasize that it is not because of the chemical equilibrium, I am calling it a phase equilibrium, but in reality the condition of phase equilibrium also requires the condition of thermal and mechanical equilibrium. So, now I can extend this argument further, and let us say now we have some p phases, right. This p can be more than 2. Let us say you have 5 phases or 6 phases containing some c components. Again, the components can also be more than 2. You can have 3 components, 4 components, any number of components. Now, I can extend this argument and say that in order for the phase equilibrium to happen in this system, the temperatures of all the phases should be the same, the pressures of all the phases should be the same, and the chemical potential of every component should be the same in all the phases, right, component by component, right. And what we have also said earlier, that the chemical potential has to come from where? It has to come from the equation of state or some kind of property relation that is coming from equation of state. So, you will also have to figure out the chemical potential from the equation of state. And finally, in each of these phases, I can define some mole fractions xi. Let us say for phase 1 it is xi for phase 1, and here let us say xi of phase 3, and clearly since it is a mole fraction, so it should sum to 1 in each of the phases, right. So, I can define independent compositions for every phase, and whatever mole fraction I define for components in each phase, if I sum over the components, it should go to 1, because that is the definition of the mole fraction, right. So, this gives me these equations which I now need to together consider in order to consider the phase equilibrium for a multi-phase multi-component system. So, we have p minus 1 equations coming from here. Why p minus 1? Let us take an example of p is equal to 3. So, we have T1 is equal to T2 is equal to T3. That is essentially two equations, T1 equal to T2 and T2 is equal to T3, right. So, therefore, in general this is P minus 1 equation, same P minus 1 equation for the mechanical equilibrium, and this we are again having a P minus 1 equation for each component, but we have C component. So, C into P minus 1 equations, and we have total C into P definitions of chemical potential, right, C components in each phase. So, Cp chemical potentials in total, and finally, we have the condition of summation of mole fraction in each of the phases, right. So, we have one equation for each phase. So, in total we have P equations. So, I will talk more about this idea of phase equilibrium going further and the concept of degree of freedom, but one thing that I want to tell you right now is that there are many examples where phase equilibrium does exist in the chemical industry, and in some cases even if it doesn't exist totally, it is still assumed because it makes our life easier, or as some kind of an ideal limit that we try to achieve, right. Let us say when we look at a distillation column, we have the equilibrium of vapor and liquid. When we look at absorption and stripping processes, we have an equilibrium of the vapor and liquid again. When we have a crystallization process, then crystals are forming and maybe the liquid on the top. So, there is a solid liquid equilibrium, right. And if I look at, let us say, general flash separation, then you can also form multiple phases in equilibrium, and we have an example of multi-phase equilibrium, right. So, therefore, in pretty much every separation process, we basically manifest the idea of phase equilibrium in order to separate components, just like we separated oil and water. And the controls that we are having are the temperature, pressure, and the compositions that we play around, and we therefore has to use the notion of chemical potentials in order to figure out what is the composition of each of these phases, right. So, we'll continue the discussion from here, and to summarize, I have discussed with you what is the idea of phase equilibrium, how it comes from thermodynamics, and in the next class I will go further on this argument. So, with that I stop here. Thank you so much.